All right, well, we're going to try going through some very basic bivariate methods. We're going to do a quick recap of some of the stuff that we've done so far. And we're going to build slowly with each method as it's covered in your book. So some of this is a little bit of review, and then we're going to get to some of the more advanced stuff here in the next few sessions. As a quick review, we've already discussed hypothesis testing, type 1 and type 2 errors. We've talked about the relationship between those two. We've also gone over the procedure for conducting a hypothesis test. As you recall, this includes setting up a hypothesis, identifying the null hypothesis, setting your level of statistical significance or your alpha level, typically 95%, etc., conducting the test, comparing to critical value, all of that. And we've gone over some basic descriptive or univariate statistics, measures of central tendency and dispersion. We've also quickly introduced the concept of statistical inference. And we've done this in part by focusing on the properties of a normal distribution, but we've also used things like z-scores to standardize our descriptive data, which allows us to speak to that normal population that lies underneath. So just as a review, because I'm not sure that I covered this very well before we went to break, we base our inferences on that normal distribution. It is our first choice because it has some very basic and pretty universal properties, including being perfectly symmetrical around the mean. You can identify the percentage of cases associated with the standard deviations, 1 standard deviation, 2 standard deviation, and 3 standard deviations out. You can identify the probability of values occurring underneath that curve, so you can identify individual points under that curve. It is a linear combination of normally distributed variables, which is itself distributed normally. It adheres to the central limit theorem, which we've already talked about quite a bit. And the normal distribution is both symmetric and mesokurtic, which means that it is not too peaked, not too fat, not too thin. So we have a great deal of flexibility in using that normal distribution. There are different types, different shapes out there. That normal distribution, which is that first one, that bell-shaped curve, is the one that we tend to assume is the case for most empirical phenomena, if not the vast majority of them. There are other distributions which your samples will show you over time. You can have a rectangular distribution, very funky looking little rectangular box. Your distribution could skew to the right or skew to the left. So it really just sort of depends on your data. Obviously, not everything fits that perfect normal curve. There are lots of varieties of bivariate tests. They come in many flavors. Which test you conduct will depend in large part on the kind of data that you have. So as I mentioned before, this is sort of the choose your own adventure part of the novel. So for instance, and this is something I did not really talk about very much before we went to break, but if you have a question that involves a mean or an average, you would need to rely on a t-test or an f-test. So let's talk about what that entails. A t-test typically is understood as a test of two means. There's a lot of different ways in which you can conceive of a test of means. We're going to do it here in just a moment, so we'll walk through this pretty quickly. The basic formula for conducting a t-test is as indicated here on the slide. A t-test has you conduct a comparison between a specific mean, that's that x bar that you see there, the mean that is being tested, which is compared to a hypothesized mean, which is that mu value. So your mean that you're testing minus the hypothesized mean over the standard deviation, which is also over the square root of n, which, as you always remember, n is the number of observations. If you have two means, you are conducting a t-test. If you got more than 2 means, you would be conducting an F-test. We're going to spend a lot more time on this in a bit. I break these two up for a reason. You'll see why later. But an F-test, sometimes known as an analysis of variance or ANOVA, is structured very differently, as you can see right here from this equation. Very quickly, I'm just going to tell you that that equation means the total sum of squares is equal to the explained sum of squares plus the unexplained sum of squares. Sometimes it's referred to in your books or in other places as the total sum of squares equals the between sum of squares plus the within sum of squares. We'll return to this later, but I did want you to get a sense of the fact that these are both tests of means. They involve mean or average data. When would you use a t-test? So let's say you have a hypothesis about college students and their approval or how they rate liberal candidates. Let's say you hypothesize that college students rate liberal candidates higher than the rest of the voting population. In this case, the mean that you're looking at here for your data, the mean that you're testing is 52. You've conducted a poll and you have found that 52% of those college students rate liberal candidates, or they rate liberal candidates at a 52% level. And you're suggesting that that is higher than the voting population, so your hypothesized mean in this case is 50%. So you set up your equation so that you put your 52, and you're going to subtract that from your hypothesized mean, which is 50. You'll plug in the values. In this case, your standard deviation is 5, and your n size is 25. So you've asked 25 people about this particular question. If you kind of go through, I don't know if I can... So if you look, as you plug in the values and you calculate this out, you get a t, your test statistic, of 2. All right, so you've got a 2. Now what? Well, as you might recall when we talked about the steps of creating a hypothesis test, one of the things that you'll do is compare your test statistic to a critical value. And I mentioned this before, that Stata stores all these tables of critical values inside its memory banks. For a t-test, you can actually find that student's t distribution, which is where you'd get the critical value, in Appendix B. So if you have your book handy, this might be a good time to take a look at that. And I'll show you in a second, or I'll talk about this in a second. So here your hypothesis, just to summarize, your hypothesis was that college students rate liberal candidates higher than the rest of the voting population. You have conducted a t-test, which is a test of 2 means. You have conducted a two-tailed test, which means that you are assuming that error lies in both ends of that normal distribution, right? So error could be located higher or lower. All right, so you've conducted a two-tailed test. You've already set your level of significance to the 95% level, so you're looking at the 0.05 level of statistical significance, and you're looking at degrees of freedom, which if you take a... Hold on a second. Sorry about that. If you look at Appendix B in your book, it's actually on page 346. If you look at the top of that appendix, and I'm sorry I can't point this out better because I'm not quite sure how to get this picture up. If you look at the top, it says alpha level for a one-tailed test, and right underneath it, alpha level for a two-tailed test. We typically do a two-tailed test. We'll talk about this a little bit more in a minute, or probably in the next session. We typically do a two-tailed test because we don't know where the error is going to lie, if it's going to be higher or lower than what we had hypothesized. It's usually the safest bet. So if you look at the alpha level for a two-tailed test, you'll see the 0.10, 0.05, 0.02, and it just keeps going. We've picked the 0.05 level, so we're going to look down that column. You'll see a whole series of numbers. The very first number that you see is 12.706, right? And that corresponds to 1 degree of freedom. So let's talk about degrees of freedom for a second. Degrees of freedom are defined differently in different tests. In this particular test, they're defined as the number of observations minus 1. Right. So we have, in this case, an n of 25. So 25 minus 1 is obviously 24. So if you slide all the way down to where on that first column it says degrees of freedom, if you go down to the 24 degrees of freedom, and then you move your finger all the way over from the 0.10 level of significance to 0.05, you'll find that the number there is 2.064. Did you find it? Take a moment. If you need to, pause and take a look, see if you can find it. If you found it, great. What you just found was the t-test critical value. And that t-test critical value is now what you're comparing your test statistic to. In this case, your test statistic was 2, right? So what is the decision now? Well, it turns out that if your test statistic is equal or greater than the critical value, then you have a statistically significant finding, which means that you have found that there is, in fact, a difference between college-age voters and their rating of liberal candidates compared to other voters. If you find no statistically significant difference, then there is, remember, we have to accept the null hypothesis that at that point there is no difference between college-age voters and the rest of the voting population. All right, so far so good. We're going to stop here. The next session, we'll talk about different types of tests that I started to touch on right before we went to the break. All right, see you soon.